So you've seen absolute value function stuff before. So this first little bit is review. Anybody remind the class what the absolute value, what that means, what that does? Yeah. Yeah, just all it's looking for. You could think of it like the length of something or the measure of something. So we don't care about direction. We don't care if we're going positive or negative. We just care about how far, right? And so the absolute value of a positive number is just the positive number. Whereas the absolute value of a negative, that's just itself. It doesn't do anything. Taking the absolute value of a positive number has no impact. Taking the absolute value of a negative number flips it to positive. And so it has this interesting little characteristic that's maybe unique so far in mathematics, where it's like, if it's positive, we do nothing, but if it's negative, we multiply it. You could think of it like this, right? You could think of it like we're multiplying the value by -1 because that flips the sign. But we only do that if it's already negative. So that's why it's kind of strange. Like, we don't just multiply all values by a -1 with absolute value. It's not the same as multiplying by -1 because we only do it in certain cases. So it's kind of strange that way. It's kind of unique. And okay, so then the absolute value of -17, very easy. These are easy questions. What we're doing today is a little bit harder than that. That's not what I mean by it's easy. Absolute value itself, taking the absolute value of something is very easy. But then working with it and doing stuff with it does get a bit more challenging. Okay? So what about something like this, though? This is where it starts to get more interesting. Now, you graph these in grade 11. But you graph with transformations, and we are going to do a little bit of sketching, a little bit of graphing, but we're going to do it in a different way. Okay, so but it can be useful to still think about transformations, but you will notice that we think about it a different way. And it's really interesting how we think about it in grade 12. And in the next unit, we do some graphing. And again, it's like related to something you do in grade 11, but we do it in a really different way, in a really neat way. So that's something to reflect on maybe. But what about 2x minus 6? Because this is an expression. Is it negative or positive? So this is the tricky part, is the four little examples that we did above. You can see if it's negative or positive because it's just a number. It was just a value. Is it negative or is it positive? But what about this one? Jason, what do you think? Depends on the value of x, right? But the absolute value of that expression would be the same way. So we're going to write this. If it is less than 0, then the expression becomes negative 2x minus 6, right? Which is negative 2x plus 6. Like, we could actually put that negative sign through. I should have left a little bit of space there. Not that important. And then if it's greater than 0, then it's just 2x minus 6. It's just it. It doesn't change. It's just the expression. Yes.
If it is 0,
yes. That, although yes, it is, but there's more to it than just a simple yes. What would happen at 0? Which one is it equal to? It kind of depends on some different things, like they're going to be different cases. But for this, when we see it graphically, they're both at 0. It's both. It won't make a difference which one we do, right? Because the negative of 0 is still just 0. That won't actually change it. But anyway. Okay, so I left a little space here on purpose. If what is less than 0? Well, the whole thing inside the absolute value, not x. It's not if x is less than 0 or if x is greater than 0, right? It's the whole thing inside. Okay? So in this case, it's 2x minus 6 if 2x minus 6 is less than 0, or if 2x minus 6 is greater than or equal to 0. And what does that mean? If 2x minus 6 is less than 0, what does that mean? Yes. Yep. So can anybody come up with a value of x that would work? 2 times 1 is 2, minus 6 is negative 4. Good, 1. What's another value that would work? 2. What's a value that wouldn't work? Somebody else. This should be easy. Yeah, that'll give you 0. What else? How about 100? Like, pick something easy. Come on, folks, think. Like, try this yourself. 2 times 100 is 200 minus 6. Yep, that's positive. So 100 is going to be over here. What did we say? 1 and 2 is over here. But, like, where's the crossover? Like, where does this become important? Well, how do we figure that out? Move the 6 over. And so 2x is less than 6. Divide both sides by 2. When x is less than 3, we multiply the whole expression by a negative. When x is greater than or equal to 3, we could leave the expression alone. Does that make sense? It makes sense usually for what we're going to do with this to do that, to simplify it to where is x going to be? Not the expression. We start with the expression, yes, but what we want to know mostly about x. Okay? Any questions about that? Kind of just thinking about stuff, just noticing stuff here. We're not really doing anything yet. Okay, so just to summarize, if the quantity of the expression, whatever it is, it might be a number, right? It might be a positive number, it might be a negative number, it might be an expression, and then that depends on what x is or what we sub in for the value for the variables. But if the quantity of the expression inside the absolute value sign is negative, this is like fill in the blanks, although I don't know if I left enough space here for me, but you can. Multiply the expression, the whole expression, by negative 1. Or this, and this is what I mean before by like there's two different cases. So the absolute value of a is equal to a if a is greater than or equal to 0, and it's equal to negative a if a, capital A, is less than 0. A represents some expression, something. This notation right here is an important notation called piecewise functions, where we think of a function as a whole, but its representation includes different kinds of functions. What would be an example of this? An oven heating up to a particular temperature. Anybody in here ever use an oven before? So your oven has like a preheat setting. So you preheat it. Was that a silly question? You preheat it to 400 and it ramps up and the temperature goes up. But when it hits 400, the oven clicks off and it does something else. So the temperature of the oven as a whole is like a function, right? But the graph would require maybe a diagonal line and then a horizontal line or something like that, right? The lines, it would be like different graphs. Does that make sense? That's a piecewise function. Anyway, not super important right now. You'll see why it is kind of relevant, but that's an important notation that we have like different cases. And we say if A is this, we use this one. If A is this, we use that one. Kind of interesting. Okay, so here's one of the things we are doing today is sketching some absolute value functions. the first one we're going to sketch looks kind of like something you may have sketched in grade 11, although it's not quite in transformation form. But we're not going to use transformations. We're going to do something different because we're going to understand a little bit more about the graph by thinking about it this way. And it's just another way of doing these things. This one you could do with transformations for sure. You'd have to factor the 3, right? So what's one property of all graphs that's really important? We used this in the last unit a lot when we were sketching. Something that's important about graphs just in general. Yeah, all of the intercepts. So does anybody know what the x-intercept of this is? 2 over 3. How'd you get that? And we can kind of like ignore the absolute value signs. In this case, it kind of looks like the polynomial thing where it's in brackets and each set of bracket is going to be an intercept, right? So this one's 2 over 3. Like if we look at this one, the intercepts are going to come from each bracket kind of thing, right? So that's same as what we've been doing. And what's the y-intercept? Ooh, this one requires a little bit of thinking. 2, very nice. How'd you get that? So in this case, we absolutely had to consider the absolute value bracket. So you could show this. So the y-intercept occurs when x equals 0, right? This is a way that you can always find intercepts. And in this course, we learn how to solve equations. So solving an equation means like if I have a whole bunch of brackets and they're equal to y, but if I want to find an x-intercept, I set y equal to 0. Now I'm solving an equation. This is what we've been doing, solving a polynomial equation. The same as finding the intercepts of a graph. See how it's all related? Our understanding of the function and intercepts and roots and answers to equations, like they're all talking about the same, all different ways of looking at the same kind of thing. Big idea for this course, that right there. Okay, so, get rid of that. Now, absolute value of 3 times 0 minus 2, which is 0 minus 2, so the absolute value of negative 2, which is positive 2. So that's really important. In some cases, that may happen. In some cases, it might not. Okay, so but I'm going to graph this in kind of a strange way. Okay, so I'm going to try to mark negative 2 and positive 2. I'm going to kind of mark them like, and I'm going to think about where 2 would be over here, just to give me some frame of reference so that my sketch doesn't look absolutely terrible. And I'm going to think about something. Actually, here, I want you to do this. So I'm going to give you a second to do this on your own. Think about this x-intercept, okay? And think about this graph from grade 9. How do you graph that? And I want you to do that. Okay, with a pencil, don't use a pen. In case you make a mistake, I want you to be able to fix it. I want you to try to do that. So go ahead and do that right now. People think it's not fair if we ask them to do things from previous years without like reviewing it or covering it. But oh my goodness, no, like graphing a line is something you should just be able to do and need to be able to do. And it's going to come up again in this course. That's a really straightforward process that we should have a good idea of. So here's your chance. How do we do? How do you do it? Can anybody help with that? You remember? Okay, good. What's the other really important part of a straight line from grade 9? So it passes through -2, okay? So it's going to pass through there, and it's going to pass through like 2/3, so a little bit less than halfway through. But what's the really important slope? Do you remember that? Rise over run. Do you remember slope? It's very important, okay? And it's like huge for stuff we talk about a little bit in this course we touch on, and we're going to talk about lines and graph lines later on. And then if you're taking calculus, oh my goodness, slope is like almost the most important thing, especially when you're first learning calculus. Thinking about slope is like really important for calculus. It's a simple idea, but we look at it in a whole new way. So anyway, okay, so it has a slope of 3, which is 3/1, so a rise of 3 and a 1 of run. So it's going to put one of my points right here, and I'm going to try to draw this line looking something, it's kind of hard to draw something. Yep, that's pretty good actually. Kind of hard to draw with a ruler on my screen, but do my best. Okay, how's that look? But that's not the graph we wanted. What happens, we want the absolute value of that. So what happens as this line is coming down, once it hits 0? Cassidy, what do you think? Yes. Jason, what were you going to say? Basically the same thing. What exactly is it going to look like?
It's going to look like you took everything that was underneath 0 and converted it.
Yeah, we just do reflection, right? It's going to just look like it hits, and instead of going below, it's going to reflect up to the top. That'll always happen because it's just the absolute value. The value is going to be the same. If I go down, like, look, we did it with the y-intercept. If I go down to -2, I'm actually going to reflect up to +2. So this was actually the reason why I wanted you to make sure you use a pencil, because I'm going to change this to a dotted line. That's what the graph would do, but it actually reflects and goes up like that. So it looks like a V. Megan called it a V before. Kind of looks like a V, right? And it can go like this and do all these things. Okay? How do we feel about that? So we kind of thought about the original graph that was inside the absolute value brackets. This is one of the things we're talking about today, okay? Is sketching. And so basically what you want to do is look at what's inside the absolute value, think of what the graph of that is, and actually basically graph it. But then we're going to take all the parts that go below and reflect them above. That's how we're going to do it. One last thing I want to think of. What was it? Oh, important to notice that what we're sketching today and what we're talking about basically in grade 12 is a special case where the whole equation is like y equals absolute value of something, some expression like a, okay? There's no +5. If there was something outside the absolute value sign, what would that happen? That's a vertical shift up, and it wouldn't, if that happened, it's not going to reflect on the x-axis anymore. This would actually reflect on the line up at 5. So you could do some of the same stuff. We're not going to really, but you could do the same thing about changing where you visualize the reflection, but it would change things a little bit in some different ways. So notice that these are certain kind of special cases that we're looking at. Does that make sense? Okay, let's move on because we got lots to do. Let's do this next one. So we're going to look for the intercepts. What kind of a function is that inside the absolute value? Yeah, degree 2, so quadratic. So it's going to be a parabola if we ignore the absolute value part. Okay, So the x-intercepts are, you should be able to do this. And the y-intercept, three. So if I put a 0 in here, I get positive 3. I put a 0 in here, I get negative 1. I multiply those together to negative 3, but take the absolute value to give me 3. Okay, so I've got negative 3. I've got positive 1. And I've got a y-intercept of 3. But I'm going to mark the negative 3 as well. And my parabola would open upwards. So let me see if I can do a good job of this. I would come down like this. Whoop, I already messed it up. I would come down like this and then go up like that, right? But this whole part that's under actually gets reflected above. Whoa. And I've got to go up and come down like that. There we go. Yeah, that's not bad. That's nice. Does that make sense? See how it's like a parabola, but everything that's below the x-axis has just been bumped up above. Kind of interesting. So this graph is like the combination of two different graphs. Because I could think about this parabola as well. That's facing downwards. Like that's a separate function. So when I'm between these values, I'm using that function. When I'm outside those values, I'm using the original function. See what I mean by like you kind of think of it as a combination of two functions? Okay, let's try one more. How in the world do we graph that? I don't think we know how to do that, do we? We don't know how to graph. Of course we know how to graph this. That's what we did for an entire unit, people. Come on. Didn't we? Well, how would I graph this? How would we start? Megan? Yeah, we got to factor it first. So this is the thing, like, oh, but it's absolute value. Why are they the same? This is where, I want you to really start trying to think about these things on your own. I just told you, we think about the graph of what's inside the absolute value and we reflect everything up. So if I can graph what's inside, I can graph the absolute value of it. So I get this. And what is that? Okay, so again, I've got x-intercepts of 0 and positive and negative 2. And my y-intercept is, it doesn't matter if you use the this one or this one for the y-intercept, right? You could use any of these, and often the expanded form would be the easiest. But in this case, what's the y-intercept? It's 0, right? If you have an x-intercept at 0, you got a y-intercept at 0. Okay, good. So, I've got 0 and positive and negative 2. So notice our sketches, we're labeling the x-intercepts and y-intercepts. That's always important. We're stating the x-intercepts and y-intercepts before we do the sketch. That's important. And this one, now I need to think about a cubic. So where does a cubic start? Like, what do we need to think about? Leading coefficient. We're just thinking about, I'm just going to think about this graph. So it's a positive leading coefficient, because people are going to confuse themselves and say, well, it's a positive leading coefficient, but it's in an absolute value. So how does that change it? No, we're just thinking about this graph. And then we're going to reflect. So it starts in the bottom left quadrant, quadrant 3, and it's going to cross over again and go off up into quadrant 1, right? So it's going to come up like this, and it's going to go like that. Whoop, that was not great. And then it's going to go down below, and then it's going to go up like that. But I'm going to take those parts that are below and reflect them above. And try to make it look like it's reflected. Like this line here would curve like this, so this line here should curve like that. Not in that much. I'm embellishing, right, to demonstrate what I'm talking about. Like it doesn't go off like that, or it doesn't go like that, or anything. Right? Try to make it look nice. Try to reflect it. I think it's really important to try to sketch the real function first, or not the real function. Sorry, sketch the non-reflected one first. Like do a nice sketch of that, and then try to reflect the parts. I think that's important. Any questions? So that's one of the things we're doing today is sketching. And so basically anything you already know how to sketch, you could now sketch as an absolute value as well, as long as it doesn't have that shift up or down. Although that shift up or down, I mean, maybe that would be some way of challenging you and making you think. I don't know. Questions, questions, questions. We got to move on to the next thing we're doing today, which is solving absolute value equations. And what I notice is the left side of that is the same function that we just graphed. Is that right? 3x, the absolute value of 3x minus 2, we just graphed that. So we're going to graph that again and equal to 5. So we're going to consider the graph. So go ahead and graph it again. I think another sketch is appropriate as opposed to using the one that we did before, because we're going to scribble on this a little bit. So I put a point at -2, and I went up 3 over 1, up 3 over 1, down 3 over 1, so I can get a nice graph here. Oop, what happened? Oop. Something weird going on here. And then we had the reflected one. So this reflects up. This point would reflect up, so I should have another point up there. And I am putting like a dotted line for both. I'm just going to fix this and change it. I hope you can see that okay. So the red graph is y equals the absolute value of 3x minus 2. And I got to use a totally different color now, so I'm going to use black. I'm going to graph the line. This is line y equals 5. And so where those graphs overlap is the solution to that equation. Okay? So we've got two solutions. And one of them is obvious, and the other one is a decimal. We could figure out what it is if we wanted to. We're not going to do it this way, but don't be confused about what we're doing right now. I wanted to get this down. I'm going to talk about a couple of things. Everybody okay? Regraphing this? Okay, put your pencil down and watch for a moment. Here's a note about the two branches of this graph. And even if you don't get a chance to copy this down right now, don't worry too much about it. You can get it after if you want. But so the branch on the left that has the blue dotted line below, okay, that branch looks like this. Whoops. Yeah, there we go. What is that? This is the graph. This is y equals negative 3x minus 2, right? So that's like negative 3x plus 2. It has a y-intercept of positive 2, and it's got a negative slope. The slope is the same, though. It's 3, so it's the same steepness, but it's leaning the other direction. But that's what that graph is. And this function uses that graph after it passes through, coming from this direction, it passes below 0 at that x-intercept, and then we start using this graph, right? So we use this graph at the x-intercept. Our actual absolute value function uses that graph when 3x minus 2 is less than 0, which is when x is less than 2 over 3, right? That was our x-intercept. The other part is this graph that looks something like that. And this is just y equals, remember, we actually graphed this. 3x minus 2. So there's my x-intercept. So we use this line in the case where 3x minus 2 is greater than or equal to 0, and when x is greater than or equal to positive 2 over 3. The x-intercept of 2 over 3, right? So I'm thinking about, in one case, so when I do this, okay, I've got two intersections. When 5 passes through this graph, and when 5 passes through my other graph. So when 5 passes through this graph, and when 5 passes through that graph, like two separate graphs. We're taking a long time about this. That gives you an idea that this is really important. Everything we've done with absolute values, even sketching them, all of that, we had to break it up into two separate cases. Like we had to think about, well, there's this one that's just this line, but what's this other branch going to be? And remember how I said this is very different from what you do in grade 11 where you just do transformation, you just memorize the base absolute value v and you just transform it. That's not really going to help us with what we're going to try to do with this stuff. So that's why we're doing it this way. We have to break it into two separate cases. Do we get that? Spent a long time talking about that because it's a big deal. And when did those two cases, like when do I know which case to use? When it crosses the x-axis, right? So when there's an x-intercept is where a line would cross the x-axis. So I flip to my other case. So thinking about the graph and thinking about how to sketch it, to graph it, you got to think about sort of two separate lines. In some cases, I'm using the negative of what was in the absolute value. In other cases, I don't. How do I know when to use which case? When we're at the x-intercept. But that's what the graph looks like. This equation is not a graph. We're using the graph to add some understanding, to infuse some understanding, right? But now what we're actually going to do, so I'll give you a second to write that down because I think you probably do want a copy done, is how do we solve these algebraically? Everything we've talked about with absolute value from the very beginning, we had to split up into separate cases. When we're dealing with an expression, different values of x will make it negative or not. So in the case where it's not, something's going to happen. In the case where it is negative, something different is going to happen. It's like the graph of a different function. This is the problem, I guess, with absolute values is we have to be the one to consider the case. There's no button on our calculator that will know which case to use. So we have to think about which case it is. We have to be the ones thinking about that and taking care of that. So to solve algebraically, we split into cases. And the cases are going to be where the function is 0 or the x-intercept. Again, notice how it's important that these equations that we're solving aren't transformed plus 5, where it doesn't hit the x-axis. That would add some complexity. You could do it. Your intuition would probably allow you to do it, but just notice that for now, at least, that's not what we're doing. So we split into cases, which is where the function is 0. Think about that as the x-intercept, I think is really helpful. We'll consider the case which goes below the x-axis and take care of it. What do I mean by that? Not like kill it or eliminate it or something weird like that. I mean like just multiply by a negative, right? So whatever it is, we multiply by a negative to reflect it. That's what happened when we did absolute value up here in the very beginning. In the case where we had a negative, it was like we multiplied by -1. Or even if I have an expression in the case where I'm multiplying by a negative, or where I'm going below 0, I multiply by the whole thing by -1, right? So that's what we mean by take care of it. And then you solve each case individually. It's not always 2 cases. More complex ones down the road later this week. We'll have more, but for now, today it's just 2 cases. And then you have to consider your solution. Okay, so let's take a look at this. So we are solving this. 3x minus 2 equals 5. Okay? So case 1 is where 3x minus 2 is less than 0. I think it's a really good idea to get in a good habit of starting with the negative case because it's to the left. Because a lot of what we do tomorrow and the next day is there's going to be a visual component, thinking about the graph, thinking about the function, that kind of thing, and using number lines and going from left to right will help. So that's why we start. A lot of people would start with the positive case because it's easier. But I think on the left side of your page, you want to start with the negative case. Okay, and this is where x is less than 2 over 3. So what do we do in this case? Why isn't this moving? We multiply. We multiply by a negative. Because that's what the graph would have looked like. Right? Where it equals 5. So that's -3x plus 2 equals 5. So I'm going to subtract 2 from both sides. Divide by -3. And then my other case, I just leave it alone. So I add 2 to both sides. And 7 over 3 works out. I'm going to just, you don't have to do this, the decimal version, right? So just quickly, I'm going back up to my graph. Does that fit with what we found? They crossed here where x is 1, and they crossed here where x does look like about 2 1/3, 2.3333. That looks about right visually to me. What do you think? So in the end, I don't think that's too bad. It's new that we have to think about these 2 cases, but that's just because of the nature of the absolute value function. That's a new thing. But that's not too bad. In one case, you multiply by a negative, and then you just solve. Like solving a linear equation, like that's pretty easy. And then in the other case, you just leave it and just solve a linear equation. Any questions? We're going to do one more example. But we're not doing the whole graphing thing here. We don't have to do that. We're just solving algebraically. So when 4 minus 7x is, whoops, let me try that again. When 4 minus 7x is less than 0, I'm going to move the 4 over because I have to figure out when this actually happens. Okay, this is hard to visualize. So I move the 4 over, negative 7x is less than negative 4. Divide by negative 7. What happens when I divide by negative 7? Yeah, good. What else? We have to flip the sign, so be very careful of that. X is greater than 4 over 7. So the function goes below 0 when x is greater than something. Okay? And when 4 minus 7x is greater than or equal to 0, do the same thing, negative 7x. Actually, we could do this a different way if we wanted to. It'll work out the same idea. I would do 4 greater than or equal to 7x and then divide both sides, right? Like you could do it either way. I hope you know what I mean. But negative 7x greater than or equal to negative 4, x less than or equal to positive 4 over 7. So that's going to be my x-intercept essentially, right, of that function. This isn't a function, it's an equation. But if I consider the function, that would be the x-intercept. Okay. So when it's less than 0, I multiply by a negative. And then I just solve. So negative 4 plus 7x equals 9. Add 4 to both sides. 7x equals 13. 13 divided by 7 is 13 over 7. And for this one, I just leave it. Subtract 4 from both sides. We've got our 2 answers. Last thing that I want to say, take those 2 answers, just do it on your calculator, sub them in to the original equation to see how it works. Okay, give it a try. Make sure that they both work. I'm going to hand out your homework.